Good morning. Happy Friday. We are in the midst of unit number 8, which is talking about design of systems in the frequency domain. So before I switch over to the slides, are there any questions that I can help people with before we get into lecture? All right, away we go. So last time we took a moment and peeked at the difference in the Bode plots between a simple open loop transfer function and its closed loop transfer function. And that led us to talk about system bandwidth. So that's a proxy for kind of how fast your system is. Faster systems will have larger bandwidths, and you measure your bandwidth from the closed loop transfer function Bode plot. So then I think the natural question is, what can we learn from the open loop transfer function Bode plot, or the open loop Bode plot, as I'm going to call it? And I think there are markers that you can look to that what have we learned from open loop stuff before? And one of the biggies was we started all of our root locus diagrams with the open loop transfer function. And we were able to conclude a lot of things about the closed loop system just from the open loop transfer function. So it's not a ridiculous question to ask. I'm just asking it in the language of frequency domain now. So let's consider the question of closed loop stability. And so we have a couple of different tools for this. On the left, I'd like to, well, let's see here. Yeah, so I'd like to run through kind of what we know already about determining stability with the open loop transfer function. So here, the loop transfer function is just k over s times s plus 1 quantity squared. So if we were to do this problem a couple weeks ago, we would say there is an open loop pole at the origin, and there are 2 open loop poles at -1. And so then we might ask ourselves, okay, where for various k's, where are the closed loop poles, and are they in the left half plane or are they in the right half plane? That is the crux of it when it comes to stability questions. So let's ascertain what parts of the real axis could be in the locus, and I think everywhere to the left of the origin actually is in the locus, right? Because we always have an odd number of things to the right once we cross over the imaginary axis here. So that means there's going to be one closed loop pole traveling west, and there's going to be one that departs -1 heading to the east, and the one from the origin will depart heading west. So these two we're going to have to break away. We also know that there will be 3 asymptotes, and when there are 3 asymptotes, they're always at plus and minus 60 degrees and 180 degrees. So that also tells us that because the asymptotes cross from the left to the right, that we will have a crossover point, a point of instability. So let's, well, I mean, we can draw that in too. The center of mass is the average of these locations. So the average of -1, -1, and 0 is -2/3. So we've got a center of mass right there. That's I don't even know what pen that is. That's a new one. Okay, and we get 60-degree asymptotes. Is that a rainbow? Okay, I don't know. I'm sorry. Why would anyone use that? I guess I just used it, so who knows? Okay, so the question I would like to ask is, at what k value do we get instability? We could then calculate a breakaway point. I think it would probably be somewhere here. And so the question is, what is that location? And at what k do we get our closed loop poles at this location? And that would tell us about stability, right? So the technique that you've learned so far is set the open loop transfer function equal to -1 and evaluate it at j omega. That would make sense. So L, when s equals j omega, has to be -1. So that would mean this equality is the definition of a closed loop pole, and this equality means that closed loop pole is on the imaginary axis. Okay, so that would give us the crossover point. Okay, so let's go ahead and do this. We get k on top of j omega times quantity, j omega plus 1 quantity squared. So what could we do here? We could say this is k on the left, and it's negative j omega. And then I'm going to FOIL out what's inside here. So I get 1 minus omega squared plus 2 j omega. And then we get two equations out of this. We get the real parts and the imaginary parts. Hold on. When I at home here, when I start up my my computer in the morning, it likes to grab all of the Bluetooth devices in the house, including my wife's wireless mouse and keyboard. So I have to relinquish them to her. Okay, cool. Now I'm back. So, okay, I want to distribute the, do I want to do that? Nah, whatever. So let's take the real part. The real part of the left is k. The real part on the right is when I take the j omega and I multiply by the 2 j omega. So that gives me 2 omega squared. The imaginary bit on the left is 0. There's no j's over here. And then I get negative omega times 1 minus omega squared is the imaginary part of that equation. Okay, so this equation has two unknowns in it, so I don't want to really start there. This equation only has one unknown in it, so let's start here. So this means this is solved for omega equals 0, but also omega equals plus or minus j. Sorry, omega equals plus or minus 1, my bad. Okay, so that means that we can erase this question mark and this question mark. And so we've just solved that this occurs at +1 on the imaginary axis, and this occurs at -1 on the imaginary axis. And those are the two that I'm interested in. So with those two solutions, I'm going to plug those in here, and I'm going to get that k equals 2 at these points. So this is when k equals 2, and this is when k equals 2. All right? So that tells me that if k is ever less than 2, the closed loop system will be stable. And if k is ever greater than 2, the closed loop system will be unstable. And all of that was derived using the open loop transfer function. So that was largely review, but I just want to point out that we could find the crossing over gain via this kind of root locus technique. Are there any questions on that? Okay, so now let's take a look at that same question, but from the frequency domain perspective. And the key here is this line right here. Because if I evaluate my Laplace open loop transfer function at j omega, this is exactly the Fourier transform, isn't it? It's evaluating a Laplace transform at j omega. And so this is equivalent to the Fourier transform equaling -1. So how can we act on that? We are looking for when L of omega equals -1. This is not always going to be true, right? There's not always going to be an omega that does this. There's not always going to be a k that does this. But what this is saying comes in two parts. It's saying that the magnitude of L has to be 1, and the phase of L has to be plus or minus 180. Right? That's what a complex number equaling -1 means. So let's take a look at the Bode plot for this system. So I'm gonna skip the k for now because I can add the k back in later because the k just will represent a constant offset in our magnitude plot. But let's do the okay, let's get our frequencies lined up here. So everything pretty much happens at omega equals 1 radian per second. 1, 0.1, and 10. This is the log omega axis. And so we'll do the components in green. It's kind of been the standard so far. And let's put 0 dBs. Let's put it up here. And let's go ahead and make these plus 20 and minus 20 dBs. Okay, so the integrator is a constant slope that passes through 1 radian per second, comma 0 dBs. And it looks like this. And continues on that slope in both directions. So here is the open loop integrator. The real poles, there are 2 of them, and they are repeated. So that's fine. That actually makes our job a little easier. Each one of them looks like this. So there are 2x of these real poles. All right, so let's also do the phase as well. And the gain here doesn't affect the phase at all, but we can say that this will be the minus 90 degree line, this will be minus the 180 degree line, and this will be minus 270. So the integrator, and I'm just going to do the phase all together at once here. So we'll do this color. So the integrator gives us constant minus 90. And then each of the real poles gives us 45 degrees per decade down. But since there are 2 of them, we get 90 degrees per decade. And they each last for 1 decade on either side of their pole frequency, which is 1 radian per second in this case. Okay, so this is the overall phase of L. At low frequencies, it's minus 90 degrees. At high frequencies, it's minus 270 degrees. At 1 radian per second exactly, it's negative 180 degrees. Okay, so let's now try to combine the magnitude curves. And I want to start with setting k equal to exactly 1. All right. So if k is exactly 1, it contributes 0 dBs of addition or subtraction, which means that all I have to do is add the green curves that I have, and I'll be done. So let's overlay this. This is 20 dBs per decade at low frequencies. And then as soon as it gets to 1 radian per second, I've got 3 negative 60 slopes. So I have to go down here to 20, 40, 60. Okay. So then this is the magnitude of L of omega when k is equal to 1. Questions on that? All right. So tell me, is this system unstable?
It looks like it's going to be going downwards forever, but it's also going to be going upwards to the left. I guess until it reaches 0 or the axis.
So remember that to be unstable, we need a pole, well, to be marginally stable, we have a closed loop pole on the imaginary axis, which is actually this condition here. This is a condition for marginal stability, if you like.
So is it the up and to the left telling you that it's going to be marginally stable?
No, I'm saying that this is an exact point on the frequency axis, this omega. And I want you to see that we have that point right here. Right? There is an omega equals 1 in this case, where the magnitude of L is 1, right? 0 dBs equals a magnitude of 1. And there's an omega, that same omega, with a phase of minus 180. Now this should be problematic for you, because this is not what we saw in root locus. Okay, so let me point out the problem here. There is a frequency. It happens to be 1 radian per second in this example. There is a frequency where the Bode plot of the open loop transfer function tells us that the magnitude of the open loop transfer function is 1 and the phase is 180. Those two things together, those two facts, suggest that this system is marginally stable. But if we go back here, this diagram suggests that when k is 2, we're marginally stable. This diagram was created assuming k was 1. So, which one is lying to you? That's the question.
Aren't we using the straight line approximation, so it's not 100% accurate?
Very good, very good. If I were to create the 3 dB correction here, so actually let me see if I can zoom in, that would be super helpful. Yes, this you can't do on a whiteboard. Okay, so if I were to include the 3 dB correction here, then each of these green kinks would actually be 3 dBs down. And since I have 2 of the kinks, then technically speaking, this, at 1 radian per second, this ought to be 6 dBs low. Okay, so Jared was correct. It was this diagram that was lying to us. So now there is no frequency where both the magnitude and the phase criterion are satisfied. Okay, so one more time for those of you who didn't catch that the first go round. Each of these poles should be minus 3 dBs at 1 radian per second. But since there are 2 of them, then we get down to 6 dBs below. (60 dBs below 0). Okay, so that's all well and good. That means that for this k, there is no frequency for which both of these are satisfied. Which means that for this k, the system is not unstable. But given this picture, we can actually figure out how much it would take to make the system unstable. Do you follow me there? What would I have to do to the magnitude curve to recreate that kind of 0 dB and minus 180 degrees of phase at the same frequency? What would I have to do to it?
Make k be an overshoot of, or make k be an offset of plus 6 dB.
Exactly. I could lift this blue curve up by 6 dBs. So if I lift magnitude up by 6 dBs, and that can be accomplished by increasing k, then I can get one frequency, omega, it'll be omega equals 1, will give us 0 dBs and, crucially, negative 180 degrees of phase. Now there is another way that we could actually make this system unstable, and that is leave the magnitude curve alone and play with the phase curve. So what would I have to do to the phase curve to recreate a 0 dB and 180 degree crossing at the same frequency? Because there is a 0 dB point on this curve already. If I don't move the blue magnitude curve at all, it does have a 0 dB crossing. It's right here. So what do I lift? Like, in which direction do I nudge the phase plot, up or down, to get a 0 dB and 180 degree crossing at the same frequency?
If you shift it
Down.
down, it'll
Exactly. If I were to take this frequency, tick, 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 and I were to drop the phase plot by this distance, so if I drop phase by, I don't know, what does that look like? That looks like maybe half of 45, so call it 25 degrees. Then I get this same condition where omega would be, I don't know, 0.2345. Omega is about 0.5 radian per second. But crucially, the 0 dB and 180 degree crossing happen at the same frequency. I don't really care what that frequency is. Well, I mean, I will eventually, but graphically it's fine. It's going to be about 0.5, 0.6 radians per second. Both of those things, both of those actions will produce these conditions. And it's important that you see that. Do you have any questions? Because these two distances are exactly what we're going to call the gain margin and the phase margin. So this is known as the phase margin. And just in English, this is the amount of phase that we could lose that would give us a 0 dB and 180 degree crossing at the same frequency. Analogously, this is the gain margin. And it is, in English, the amount of gain we could afford to add before we get the same condition, a 0 dB and a 180 degree crossing at the same frequency. So this has a gain margin of 6 decibels and a phase margin of about 25 degrees. Both of these are positive numbers, and that's crucial. So what do I mean by margin? Margin is, I think, is confusing to some students. Margin is it's the buffer around your page of notes, right? If you're writing on paper. It's a safety margin, right? It's the amount that you can still fudge into and still be safe. It's exactly the same idea here. The gain margin is the amount of gain that we could fudge into and still be stable. The phase margin is the amount of phase that we could fudge into and still be stable. Okay, so they are pads, if you like. And I really like this example because this 6 dB gain margin corresponds to a factor of how much. So if I add 6 dBs to something, what do I multiply it by?
Is it 40?
No, 40 is a good guess, but remember that 3 dBs corresponds to square root of 2. And so if I do 2 3 dB gains, that means multiplying by square root of 2 twice, which means we're multiplying by 2. Yes. So if I were to multiply this gain by 2, then we'd have k equals 2, and we'd have agreement with this plot. So we were able to confirm at least the gain crossover with the root locus. This backs that up. Now it's much harder to see the phase margin in the root locus plot, but it is there. I don't know if this is going to help you or not, but if I set k equal to 1, that's going to put our closed loop hole somewhere in here. So these are when k equals 1. Now, if I were to rotate the root locus about the origin by 25 degrees, then I would also accomplish the same thing. I would put this closed loop hole on the imaginary axis. Like I said, that's a much more involved operation, and it's harder to do visually. But that is what 25 degrees corresponds to. It means take the closed loop hole when k was 1, and if you rotate that around the origin by 25 degrees, you'll put it on the imaginary axis.
What exactly are you doing mathematically to do that in the other
I'm
plot?
saying L of S is some, when this is S hat there, if I were to rotate that, which means multiply it by e to the j phase margin, that would give me an imaginary number. Right, because this is a pure delay term from our ingredient list in Bode plot land. And if I were to multiply the open loop transfer function by a delay term, I don't change its magnitude, so I'm not stretching the root locus plot at all, but I am rotating it. I am delaying, I'm adding phase, or I guess subtracting phase in this case. So this would mean that we're taking the entire root locus plot and we're rotating it around. This operation is why people learn about Nyquist plots, and it's why this class is a little bit harder at this point because we don't have time to go into Nyquist plots, but this operation is much easier if you do this on a Nyquist plot rather than on a root locus or a Bode plot. So this is a kind of motivating example, is that we can, it's almost better, I would say, than root locus. We can, because we get quantifiable margins here. If I pick a gain, so again, this whole thing started when I picked k equals 1. Once I pick that value, everything is then fixed. And if I draw the open loop Bode plot, I can then measure how far away from unstable the closed loop system would be. That seems like a powerful tool. I hope you recognize that.
You can find out where marginal stability is, but what about finding where, like, because logically it's unstable beyond that, but how do we see that it's unstable?
Good. So that is tricky to see, and this method is most useful for systems that start with low gains in the left half plane and end with high gains in the right half plane. It does not work very well when that is reversed, when you start in the right half plane and you cross back to the left half plane. It also does not work very well when you start in the left half plane, cross to the right, and then cross back to the left. Those situations are much harder to see from a simple open loop Bode plot here. If we go beyond, so if we were to go out into this region, say k equals 4 or k equals 3, then what would happen to this plot? It would be raised by, well, if we set k equal to 4, then we'd take the k equals 1 curve, we'd move it up by 6 dBs to get k equals 2, we'd move it up by another 6 dBs to get it to k equals 4, and so we get something like this, where this is now 6 dBs above 0. And so now the 0 dB crossing is over here at this frequency. And we get what's called a negative phase margin. So this would tell us, because the phase is below 180 at this frequency where 0 dB crossing happens, this would tell us that the phase margin is negative, which means we could lose a negative amount of phase before becoming unstable, which means we're currently unstable. So this would mean a negative phase margin. And that implies the system is currently unstable. Likewise, if we look at the 180-degree crossing, which actually hasn't changed, now we see that the gain margin is also negative. So this represents a negative gain margin. This would tell us that the gain margin is negative 6 dBs. Therefore, we can increase the gain by negative 6 dBs before becoming marginally stable, which means we have to reduce the gain by a factor of 2 to become marginally stable. Everything I just said is included in this slide, but I wanted to show you an example and a graphical demonstration before we got into the strict definitions of these things. So perhaps it's time now to talk about the definitions. Like I said, the gain margin is the factor by which the open loop gain can be increased before the closed loop system becomes unstable. If that factor is a negative decibel value, you're already unstable. And the way to calculate it is you take the 0 dB point and you subtract the magnitude of the open loop transfer function at omega 180. So this is where these slides are incomplete because I didn't actually define omega 180. Omega 180 is defined as the frequency where the phase is 180. Okay, I mean, the subscript kind of tells you what's going on. But crucially, the omega 180 assumes the phase is 180 degrees. And this then, the magnitude of the L at that frequency tells you how far away from 0 dB point you are. In the phase margin definition, we have a similarly undefined frequency. Omega C, which stands for omega crossover, is the frequency where the magnitude is 1. Okay, so this is the called it the crossover frequency. It's where the magnitude plot crosses the 0 dB line. Just like the omega 180 frequency is the frequency where the phase plot crosses 180 degrees. Okay, so this is kind of complicated. It also suggests that it's really nice to draw your magnitude and phase plots on the same graph paper, especially just make them line up, right? Because this operation, to find the phase margin, I had to start with the gain plot and go down. To find the gain margin, I had to start with the phase plot and go up. If you draw your gain and phase margins side by side, or sorry, your gain and phase plots side by side, it's just practically harder to do. So that's why you'll see me draw a lot of my Bode plots top and bottom. Your textbook likes to do them smack on top of each other with just different colors. And I think that is, it's fine, but it saves paper for sure, but it makes things kind of messy when you start doing all these lines and stuff. So gain and phase margin are the two biggies. So I'll pause here for questions on those, and then I'll talk about delay margin.
So if the gain margin is negative, then it's already unstable?
That's correct. If either of the margins are negative, then the system's already unstable.
But if both of them are negative, then it's stable?
No, two wrongs don't make a right here. No,
Okay.
no. It's both have to be positive to be stable. If anything is negative,
okay.
It's unstable. Oh boy. Okay, so then the delay margin is getting at this thing. It means how can you physically move the phase plot up and down? Well, you can move the phase plot up and down if you were to add a pure phase delay or advance. Right? A pure phase delay only moves the phase plot up and down. It doesn't touch the magnitude plot. So the phase margin is an angle, right? It's a degree measurement, but it occurs at a certain frequency. And so the amount of delay in the time domain that corresponds to this number of degrees at this radians per second is exactly this operation. Okay, so this is, if phase margin is in degrees, and then the pi over 180 changes that to radians. So now the phase margin is in radians. And if I divide radians by radians per second, I get seconds. Okay. So this is a way to convert the phase margin into something that I think is a little bit more tangible. This is the amount of delay, pure delay, that if your system has in its loop that you're not accounting for, you could have an unstable system. There's a chat, it looks like here. So it looks like the chat question is exactly what we just covered. Is it either if the gain margin is positive and the phase margin is negative, that still means the system is unstable, and vice versa. If the gain margin is negative and the phase margin is positive, then the system is still unstable. If both of them are negative, the system is definitely unstable. The only way we can have
the phase margin is just an angle. Isn't every angle both positive or minus depending on like how you're going to measure it? Like if you have 90 degrees, you could call that negative 270.
Okay.
Is it just like
sure.
beyond 180?
Yeah, so we're doing this all mod 360. Yeah.
Okay, so if it goes above 360, then it becomes.
Well, let's just treat all of our angles as living between plus and minus 180.
Okay.
Yeah, so if you ever tell me negative 270, I'm going to automatically convert that to plus 90. Because you're right. Otherwise, there's no truth. Any number can be any other number you like. Well, that's not exactly true. Any number can be any number plus 360. So in order to make a meaningful statement about phase margin, we have to talk about phases as living in the plus or minus 180 degree region.
That makes sense.
Good point. Okay, so right, back to the delay margin. I think phase margin is tricky. It's tricky for me to understand, to wrap my head around. I am much more partial to this notion of delay margin. Chat again. What does mod 360 mean again? It means if you ever have a number exceeding 360, it gets wrapped back around. You subtract 360 from it. So think about like analog clock arithmetic. If the hour hand would ever hit 13, we subtract 12 from it and it becomes 1 again. Sure. Okay, right, delay margin. Think about what would happen if you and your friend were trying to control the amount of water in a tank. You are sitting at the tank and you're looking at the water level in the tank. Let's say that there are some holes poked in the tank and so the tank is leaky. But it's your job, you and your partner's job, to keep the water at a fixed level in the tank. So maybe we can get a picture here. Yeah. Okay, drawing time. So we've got the tank, and it's got some holes, and the water is leaking out at a rate that we're not quite sure of, which is why we're hired to keep the water level in the tank. So we're going to get a pipe here. And in scenario 1, the sensor is standing right next to the tank, and we've got a fixed line that we want to keep the water level at, but let's say the water is leaking out, and so the water is below that. And so in the first scenario, the actuator is really close. Okay, so when the sensor says more water, the actuator hears it right away and adds more water, and we come up to here. When the water level gets to the line, the sensor says less water, and the actuator stops, like closes the valve. Okay, this is a cartoonish but legitimate control system, right? There's an actuator, a person who is going to work this valve, and a sensor that is monitoring what the current process is, or what the current output is, where the output is the water level. And there's a disturbance because there's water leaking out of the tank. Okay. That all kind of makes sense. What if we have scenario number 2, where the actuator doesn't get to stand real close, but is rather 400 yards away, 200 yards away, whatever, a long ways away. So here's the actuator now. Now, because they're so far away, it takes a noticeable amount of time before the shouts from the sensor reach the actuator. Right, so now that there is a propagation delay, all of a sudden the current information isn't being acted on. It's actually old information by the time it gets to the actuator. And so what the actuator is going to be doing is he's going to be opening the valve when the sensor is already saying shut off the valve. And he's going to be shutting off the valve right when the sensor is saying open up the valve. And so what that can lead to is one of two situations. Either all the water drains out of the tank because they're not adding water when they should be, and they're adding water when they should be, or the tank overflows because they're adding water when they shouldn't be.
How is there a time delay in a circuit with like electrical stuff that happens at the speed of light?
There won't
What's
be any
causing
time
it?
delays in the analog circuits that we're dealing with. But when you start dealing with much faster systems, and perhaps digital systems, you can start thinking about there will be some propagation delay. Like if all you're doing is maintaining charge on a capacitor, then everything has to happen on the time scale of electron movement in a circuit. Now that's a little hard to think about in like realistic terms, but think about it this way. If you were going to implement, say, the DC motor control in real life, you might still, you probably wouldn't actually. You would definitely have the motor. Here's your motor, yada yada, with the shaft and spinning something. But the sensor, we are in the lab, we're using just a simple analog potentiometer. But in a more modern context, you might have an analog to digital converter. And then that would send a digital signal to a microcomputer. Which would then send a signal to a digital to analog converter, which would then be a voltage that we could send to the motor. Now, I don't know about you, but I don't know how long it takes an ADC to convert a single bit's worth of data or bytes worth of data. I also don't know how much time it would take a microcontroller to read that, process it, perhaps call from memory if it's doing some kind of integration, add to that memory bit, save that memory bit, and then send out the new signal. And then I also don't know how long it takes the DAC to take the digital and convert it back to analog. All of these have time delays associated with them. We treat them as instantaneous, honestly. But if you stack enough of these up together, it's not going to be instantaneous anymore. And so what I like to think of the delay margin as, again, it's a margin, so it's a buffer, it's a fudge factor. It tells you how much fudge you can have, how much delay you could have around the loop before things become problematic. Okay, so if your delay margin is 30 milliseconds, then you're fine, right? There is no way that a ADC, an Arduino, and then a DAC are going to combine for 30 milliseconds of delay. Not going to happen. But if your delay margin is 30 microseconds, or 3 microseconds, or 30 nanoseconds, then it becomes much more of a, we should probably start considering this. Okay, because I'm not sure that an Arduino can read and write within 30 nanoseconds. I'm pretty sure it can't, actually. But if your system is stable, but can be destabilized by 30 nanoseconds of delay, that's a problem. And it's not an insurmountable problem. You can do other stuff to fix that, but it's a problem that you wouldn't know about if you didn't know and factor in your delay margin. Does that make sense?
Yeah, that makes a lot more sense now.
Cool. Yeah, I like the tank analogy because it's like everyone has heard that it takes time for sound to travel over long distances. And I guess implicit here is that the water is actually traveling much faster than the sound would be traveling. But even if the water was traveling more slowly, then that would actually contribute more to your delay margin, or yeah, eat into your delay margin as well. Cool. What time we got here? We are out of time. Okay. So we are going to do an example next time in which we consider, is proportional control sufficient to stabilize the system? If yes, then what should the proportional control be? And if not, how can we fix it? Okay. So we'll tune in on Monday for that, and I hope that Monday will be the last day for Unit 8 as far as Unit 8 homework material is concerned. So we've got a couple minutes now. I'm happy to answer any questions if you have them. All right, well then we get a very rare occurrence. No, just kidding, not a rare occurrence.
Sorry. I've been wondering, for the telescope, I had been working on making a better controller, and then I realized after a while, I had basically just made a new PID controller, but that was in like series rather than those 3 parallel branches. Is that a bad thing to have them like 3 op amps one after another just for the 2 zeros and a pole at the origin?
Practically speaking, yeah. So I mean, whenever you get 2 zeros and a pole at the origin, you're right. That is a PID controller. The upshot of having 3 parallel op amps is that each one of them will have their own kind of voltage limits, voltage rails, and if you were to do them in series, would that?
I was wondering about the phase. Would that have any impact on like the phase of it? Because I know that you mentioned the position of some of the cutoff frequency ones that can affect the noise. And I was wondering if I go that route of having it in series, what would be the consequences?
Yeah. So if you additionally introduce a low-pass filter, like we did in lab, then if you put them all in cascade, you are filtering all of the branches, the P, the I, and the D. Where if you do them in parallel, you can put the filter only on the derivative term, which means that you get the most bang for your buck out of the proportional and the integrative term. And you're only, I don't want to say handicapping, you're only impeding the derivative, which is fine because it's only the derivative that gives you that high frequency gain. The proportional term gives you constant gain across all frequencies, and the integral term actually cuts off gain at high frequencies. So if you do them all in a string, in a line, you are impeding each of them rather than just one of them, if that makes sense.
Okay.
But I mean, you've only got 4 op amps, so I was thinking about it this morning. I think you probably could still do the parallel topology, but you'd have to do it slightly differently than how I did it in lab, because in lab, I did it with 5 op amps. and that means you're 1 op amp short.
Uh-huh.
So, okay, that brings us to 9 o'clock. Thank you, everyone, and have a wonderful weekend.